Right. Awesome. So yeah, hi everyone. My name is James Lee, and I'm leading this webinar series for 12 Labs. This is called Multimodal Weekly. For some of you who've been here before, some of you who are new, or some of you learned about via different platform. It's a weekly webinar series that we've been meeting virtually every Friday. And some of the topics that we tend to cover on a weekly basis, ranging from on the academic research side, news papers and research direction in multimodal AI as well as prediction models. We have others, entrepreneurs from different startup building innovative multimodal application in different verticals come talk to us. Since we focus a bit more on the video side of things, we have people like the developers, open source work, talking about some of the video multimodal projects that I like to share. And oftentimes we have tutorials and guides from our internal team members talk about how to use our platform and APIs. So, a big focus of some of the guests lately has been a lot more on the research side of things. Occasionally, I try to insert a bit like founders and open source speaker in here as well. But we have folks from academia as well as big tech talk about different direction on speech and audio understanding to open source multimodal LLM to model alignment to building data set for multimodal perception, right? And last week we had two partners talking about basically multimodal search and audio understanding for video production. So for the session today, we have three speakers actually. First speaker is Chia, co-founder of Eventual Computing, and he's actually a second-time speaker. I remember when Jay was giving a talk, probably like more than a year ago. I think session number 7 is number 8, if I can recall correctly. Talking about Daft data frames, and back then I always I think like been super excited about like kind of some of the progress that you guys been making with different evolution of Daft over the past year. And I think he will dive a bit deeper on this concept of multimodal data lake, which is bringing data frames into like the data lakehouse, and how Daft, the project that he's been working on, will help solve that problem. And then the next two speakers, both coming from academic background. The second speaker is Saptarshi Sinha, currently a Ph.D. student at University of Bristol, and he's talked about his research called Every Shot Counts, using exemplars for repetition counting in videos. And the speaker is going to be Yunhua Zhang, currently a Ph.D. student at University of Amsterdam. She will talk about low resource vision challenges for foundation models. So I came across both of the research from Yunhua and Saptarshi at CVPR, last month, and I think their work is super relevant to the focus on multimodal and video that we're doing at 12 Labs. So we'd love to learn about the overview, motivation, the mechanism, and evaluation, all that stuff from their work, and hopefully we can have a lot of engaging discussion with us. So with that, just one quick note on the logistic for the audience. Feel free to send your question on Zoom chat, and then the speaker can answer them after they finish their talk. So I stopped sharing my screen, and Jay, do you want to go ahead and get started? Let's aim to anywhere between like 15 to 20 minutes for each of the talk.
Yeah, that sounds good. Cool. So let me get started. So today I'm going to talk to everyone about building your own DIY, right? Built at home multimodal data lake and what that looks like. So I'll be building, don't worry, I'll be building a lot of context as we go along for those people who are not familiar with what a data lake means or what a data warehouse is. It's all very industry parlance, very industry terms, right? But I think this is also actually super useful for something that if you're building a research lab or doing in academia, I think it's also super useful to be thinking about in terms of data organization and how do you have good data sets. So a little bit of background about myself. I'm a co-founder at a company called Eventual. We are primarily building Daft today. That's our query engine, right? You can find us at getdaft.io. It's a Python-based query engine. We'll see a little bit of a demo of it later on. But prior to Eventual, I was building machine learning distributed data systems for machine learning at Freenome, which was building for biotech. So it's all kinds of, multimodal data from like genomics, right? All these weird genomic files. And then at Live Level 5, I was doing autonomous driving there. And so dealing with a lot with videos and images and LiDAR, point clouds, sparse tensors, also very much in the multimodal domain, right? So kind of along the way, figured out, hey, this world of big data, for some reason, only does analytics. Like everyone is very focused on analytics, right? How can we get the world of big data and the world of data systems to really care about multimodal and kind of these different types of data modalities as well. So yeah, the goal of today's talk is to convince you that a data lake can also handle multimodal data, right? But watch out for the many footguns. And so I'll be showing off some of the footguns that Daft will help you with. But also, like we're not there yet, right? A lot of the things we're building in Daft, slowly getting us to the point where you can work with your multimodal data in like this like table format almost as easily as you work with any other data frame, like a pandas data frame of like numbers and strings. But yeah, we're very close, and I think the future in which working with multimodal data is just as easy as working with like a table of CSVs is, I think, not too far away. Cool. So let's talk a little bit about what the data lake is. So for those who are not familiar with the term, the way I like to think about a data lake is that imagine you have a bunch of CSV files just lying around, right? Just a table of data. A data lake actually allows you to put one layer on top of that, which is just, instead of just having a bunch of CSV files, now you have the idea that, okay, these CSV files are a table, right? This table comprises of say 100 CSV files. In this case, a lot of people use a format called Parquet. It's kind of like a CSV file, but every Parquet file actually just has more information, like what is the schema of this file. Here are all the rows and the chunks, right? So it's a lot more efficient of a file format, but it's very similar to something like CSV. And so instead of just having Parquet files lying around on disk, what you usually do is you store them in something like Amazon S3 or whatever file storage you have, and then you put something on top of it called a table format, called something like Delta Lake or Iceberg. All these table formats do is that they will tell you, hey, you're looking for table XYZ. Here are all the files for table XYZ, very simply, right? So that's a data lake. That's how a lot of these systems in the wild work today. All these companies have Delta Lake tables, Iceberg tables, and under the hood, these files are just Parquet files, right? Very simply Parquet files. And then, the data lake itself isn't useful, right? It's just a bunch of files lying around. You need something like an application that can, read and write the files and do some processing. And so that's called something's called a query engine or a data engine. So some that you might be familiar with are, Spark, Trino. I'm sure people here are familiar also with like Pandas, maybe Polars, DuckDB. These are all falling under the camp of what I would call a data engine, right? And different data engines have different capabilities, but oftentimes they all are able to, well, nowadays, they all are kind of able to read these data lake formats like Delta Lake and Iceberg. So the problem though is, how do we translate this pattern into multimodal data? Right? The problem is that like Parquet, for example, isn't built very well to store images, right? Or to store video or tensors. You can, but there's actually a lot of different trade-offs you have to make, and you have to like fine-tune a lot of your storage to make it work. And so in other words, you become a data expert, which is not where you want to be, right? So the problem with multimodal data is that, first of all, on the data lake level, right, you need to have efficient storage and retrieval of both your multimodal and tabular data, right? So imagine you want to write images into Parquet. What does that even mean, right? Like big question mark, no one really knows. And then on a data engine point of view, you often need to support efficient data operations, both for multimodal and tabular data, right? So you want your normal like adding two numbers together, doing summations across the column, all of that, the normal tabular stuff. But you also want to grab say a number of pages in a PDF, right? Or height and width of an image. Like those are all operations that the data engine has to support. And so the problem is that like all the systems today don't really give you that ability, and that's why no one really has cracked this like multimodal data lake just yet. But today I'm going to show you a little bit of a demo of like how just using Daft as your data engine on top of your regular data lake with some modifications, you're really able to achieve this like feel of like, hey, I have this table of data in my data lake. It contains images, right? And then now you can do all kinds of things. You can do analytics. You can, tell me what the average height and width is across my entire data set, or like plot me a graph, right, of like height, width, and like channels. You can do data engineering. You can pre-process all of your images, do all kinds of augmentations, filter out bad images, right, and maybe even call LLMs on them. And then last of all, you can do ML AI, which is essentially all people want to do is either you run batch inference of your model on top of your data, or you feed it into training, right? That's like the two most common things. But Daft is a pretty good fit across all of these. I think strongest across ML AI and data engineering. Cool. So yeah, here are some of the challenges that we'll be facing throughout the demo that I'm about to show you. But we'll be able to just see them as I go through the demo, I think. So let's just hop into the demo real quick. Zoom in, make sure everybody can see. Okay, so first we're going to use Daft to just load a bunch of data from AWS S3, right? So with Daft, all you do is you call, you import Daft, right? Well, first of all, you install Daft like this, pip install get Daft. It's just a simple Python package. And then once you have it, you call from glob path. This will basically just glob this path and return me a new data frame of rows, where each row is a new file. And we notice that each file is a JPEG file, right? So in this Daft public data folder, I have a bunch of JPEG files just lying around. Really, really opaque right now. All we know about them is the size, right? So from here, actually, what you can already do is you can maybe even filter by the size, right? And like only get JPEG files of a certain size. What's really cool when you work with Daft, and this is, I think, really key when we work with multimodal data lakes, is that working with URLs has to be kind of a first-class native operation, because oftentimes you just have tables full of URLs, right, pointing out to images. And so all you gotta do in Daft to convert URLs to bytes is you just say, Daft, please take this path column and then run this URL download on it, right? And then you now have this new image bytes column, and that's all just bytes, very simply. And we've actually fine-tuned this across, like millions of URLs and making that extremely efficient and really saturating your machines. And so this operation of like essentially materializing your data, materializing your URLs is extremely, extremely fast in Daft. Next, Daft actually has native image types, right? So you can say Daft from this column of image bytes, run a image decode function and create a new image column, and bam, right? And kind of like 3 lines of code, you've gone from your URLs down to bytes, down to images. And Daft is doing all of the IO and data loading for you in this case. And a very common thing you might want to do is maybe create a thumbnail or resize your images, right? For either visualization or later downstream you're putting it into a model. And so Daft also supports a lot of these common functionality for images now, where you can say image.resize, and now you get these resized images. And so kind of our recommendation actually is when you store data in your data lake, oftentimes you don't want to store this entire image, right? Each image is going to be like, what, 300 kilobytes, pretty large. In the worst case, some of your data sets with much higher quality images will have, a couple of megabytes per image. That's not something you want to store in your data lake. Imagine storing a giant, like 3 megabyte thing in CSV. It doesn't make sense, right? So what we recommend instead is you just create these thumbnails and store these thumbnails in your files in your data lake, but then you just store these as URLs, right? These are the URLs. So yeah, that's why I think creating thumbnails is really, really powerful. Okay, so the next thing we can use Daft to do is Daft allows you to write all these Python functions that you can run over your columns. So I'll spare you the gory details, but I've written 2 functions. One generates pre-signed URLs. I'll explain what that is in a second, but basically it's a URL that has a short expiration time that you can then pass around and send it to different endpoints. And the second, I just wrote a very simple thing to hit GPT-4o in OpenAI, right? And with a prompt, right? What's in this image? And so using these 2 things, I can actually just call, first generate the temporary URLs, send that across to GPT-4o, ask it what's in this image, and then using Daft's utilities for parsing JSON, which is the return that you get from GPT-4o, right? These are JSON. I'm just going to parse out and grab the text as a description. And again, in like 3 lines of code, we've gone from just having these images down to making these URL calls using temporary credentials, right? And most importantly, send that across to GPT-4o, and then now we have have a description. Right, this is really crucial, I think, and something that has really changed in the last year or so for multimodal data, where you no longer have to train your own model, go through the entire life cycle of doing ML ops and all that, just to get some value out of your multimodal data. Today, it's doable in like 3 lines of code, right? Send it over, throw it over the fence, ask the some sort of endpoint to give you some results, and bam, you have like a full description of your image, which you can then use for subsequent purposes. So, okay, so we don't yet have a data lake because we actually haven't saved our data yet. So I'm just gonna grab the path, right? These are the URLs, the thumbnails, and encode them as JPEG and just store them as binary. And then I'm gonna grab the size and the generated description. And now I'm going to limit it to 8 rows and write it into my data lake, right? So bam, now we have this kind of this is my data lake, where you have this delta log in here. Don't really have to understand what that is, but this is a Parquet file. And now that you have your multimodal data lake, you can kind of read from it. You can, materialize your image thumbnail. Here I'm doing actually a filter, say filter for rows where the description contains dog, right? So now we only get rows where GPT-4o told us there were dogs in here, which is like pretty cool, right? You've kind of gone from the raw, just images, don't know what they are, to this step in kind of like a very short demo. The cool thing is Daft also scaled up in the cloud, and we do run distributed. And so if you have a distributed cluster of machines, we actually are able to scale it up on like GPUs. And so if you want to run your own models and all that, Daft supports all of that really well. But yeah, this kind of the end-to-end example. Now that you have this kind of data set, you can run kind of any analytics you want. You can, pipe all of this into training of your own models or fine-tuning of your own models and do any data engineering that you need to do using Daft. That was it for the demo, but I wanted to highlight some best practices that we saw in the demo. So first of all, we recommend using URLs for any data that's larger than say 100 kilobytes. Even if you have 1 million URLs, it's fine, right? Because Daft kind of, with that URL download utility that we have, we do a really good job of this like small file problem using under the hood, use async rust to deal with that. So yeah, store your images as URLs in your data lake, works well. Avoid materialization of your URLs if possible. So in this case, instead of downloading the data and then sending it across to OpenAI, what we did is we use a pre-signed URL, right? We just send across a URL to OpenAI, telling them, hey, this is my image. And so the data transfer actually is now between OpenAI and S3, right? Instead of coming to us and then sending it across OpenAI. So that's another really good best practice that you can think about. Don't forget your veggies, don't forget your metadata. You want to extract, generate metadata for downstream analytics, right? Things like the height of your image, the width of your image, description, captions, all of that you want to keep in the same data set as the rest of your data. And that's kind of the power of the data lake, where you have everything just kind of right there. And then the last thing is, I guess, like be careful with Parquet. There's a lot of gotchas in here. I didn't really cover a lot of them in this short session. Feel free to talk to me after if you want to talk more about Parquet. We delved very deep into this file format. But yeah, just check that you're not doing anything crazy with Parquet, especially with larger blobs. So here are some wish list and roadmap items that we are working on in Daft. So we're baking in some of the best practices in here, right? Allowing you to, for example, get pre-signed URL directly from Daft instead of writing your own Python function to do it. We also, this is really cool, I think. We want to build in a way to do like global control for making calls. So you can say, hey, like run GPT-4o, but make sure the tokens per second count is under a certain amount, right? So keep my costs under control. And then lastly, I think this is really cool. Imagine you could like do indexing of your multimodal data. You can do like, give me rows where my data frame.image is like a brown car. And under the hood, what we can do is we can do like generate embeddings and do like embedding match and search over your data set, which I think is really interesting. Yeah, and that's a wrap. You can learn more about Daft at getdaft.io. Wanted to plug also that we are hiring pretty heavily. So if you are interested in data systems, multimodal data in particular, or just data systems in general, come talk to us, and I'll drop my email on the chat later on so that everybody has it. But yeah, happy to take any questions now.
Awesome. Yeah, thanks a lot, Jay. Yeah, you also put on the email in the chat as well. Yeah, is any, maybe you have time for like 1 or 2 questions Roger, before we move to the next talk? Anyone who want to ask a question?
I think can you all hear me?
Yep.
Yes.
Okay, one question I have is, as you mentioned, multimodal data, is there videos as well that can be supported with that? Yeah.
Great question. So that's something that we're actively working on now. Videos are really interesting because they're not like images, right? Where it's just like single file all the time. Usually what people want to do is, oh, sorry. Did someone know? Oh, okay. Yeah. So usually with videos, what you want to do is, for videos, you have a single video file. What we recommend is you keep a single video file around, but then you are able to understand, okay, here are the clips in my videos, right? You might have like 1,000 clips per video, starting from a certain timestamp to a certain timestamp. And then Daft will be able to then support something like sample at 10 hertz from a video, right? And so that's something that we're looking to build into Daft in about the next month or so, and really building out kind of this idea of what does a video warehouse look like, and how do we enable all these operations like sampling of images, transcribing, doing clips of the videos, and powering the same workloads that we do today with images, but over video instead.
Awesome.
If you're interested, please make an issue. I'd be very, very interested to jam on like a good API and stuff. Yeah, we're still internally, I think, thinking about the API really deeply, working with a lot of partners in the AI domain, who are all actually thinking about video today, which is cool.
Yep. Yeah, so I think that's something we're gonna love to explore with 12 as well. I think because we focus a lot on video
Exactly.
model, right? So I think there's an opportunity here to like build our native integration with that, so that let's say someone can easily get the caption summarization in the data frames given the URL of a video file. I think that'd be a cool abstraction.
Yeah, I mean, there's a lot of really cool things you can do once you have this abstraction, right? You can do things like do sampling and then do clip embedding generation and then do a lot of like, similarity matching across embeddings. The possibilities are actually pretty crazy once you have a kind of singular abstraction of this like data frame that's performant and powerful across all different modalities.
Awesome. Well, yeah. So if anyone else made the question, feel free to just put in the chat and Jay can answer them. And yeah, please, if you can provide any like getting started resources, those things with that in the chat as well.
Yeah, I'll drop it in the chat.
Yep. Awesome. Let's move on to the second speaker. So Jay, can you stop sharing the screen, and then Saptarshi, do you want to go ahead and open up the talk?
Yeah. This. So can you see my screen?
Yes, I can see it.
So today I will be talking about our recent work, Every Shot Counts, using exemplars for repetition counting in videos. So as James already introduced me, I am second year PhD with Dima, and this was a joint work between University of Bristol and University of Twente, and like Alex Sturgey is from University of Twente. So what is repetition counting? So many of you must be familiar with the task that is called object counting in images. Like it's also used for crowd counting or people counting or counting the number of instances of a given class in an image. So parallel to that task in images, we have similar repetition counting in videos, which aims to count the number of repetitions in a video. Now this repetition can be an action or it can be a motion. For example, in this video, the person is cutting vegetables. Now we want a model that can say how many vegetables did she cut. So let's say the person cut like 3 vegetables. Or we can also ask how many slices did she make. So that both of these are repetitions, and we want a model to do that. So unfortunately, like there has been a lot of work in image counting, but video counting is relatively new and not many people have focused on it. There are some works, for example, like this was a very popular work on repetition counting. So what they do is like they create a temporal self-similarity matrix. So how they do this is like they take the video frames, they use a pre-trained encoder, they send each frame to the encoder, they get the embeddings, and then you can use these frame embeddings to compute pairwise frame similarity. So for every pair of frames, you can get similarity. So this is how you get this matrix. And then you use this matrix further in the further model to predict your repetition or period or whatever you want to ask the model to do. Similarly, there has been development in that same direction. Like this was a paper in CVPR 2022. What they do is like instead of frame embeddings, they do sequence embeddings. So they take a group of frames instead of just a single frame, and they send it to a like temporal encoder, like this 3D coordinate or whatever you can use. And they take the embeddings and compute a similar to something like they take the correlation matrix, which is basically similar to temporal self-similarity matrix, and then they use it for the period predictor, and finally they get a density map, which gives you the count of repetitions as well. But the drawbacks of this existing approach is like because they rely too much on the self-similarity matrices, so when your camera viewpoint changes, the self-similarity matrix won't be able to capture those similarity. So for example, in this video, the person is doing push-up but the camera is moving. So first the person push-up is showing from a different viewpoint and then the viewpoint is changing. So the similarity between these will be very different. It might not be similar at all. So this will not be captured and the model will not be able to calculate, capture that as a repetition. So what we propose this new model called ESCounts, which is which is abbreviation for every shot counts. So what we do is like, for example, here is a task, like given a video of push-ups, we want to count the number of push-ups the person did. But we use exemplars. So if you show a human an exemplar of push-up, the human will know how to count a push-up in a video. So we are learning a model based on this exemplar-based concept. So where we sample exemplars from the video. So during training, in the ground truth, we already know where the repetitions are occurring. And based on those repetitions, we can select one of the repetitions as our exemplar. And during training, we show this exemplar to the model and ask it to count. And if it counts wrong, then we backpropagate the error and do this. But also what we do is like we also sample exemplars from other videos of push-ups where a different person is doing push-up. So by this, what it happens is like it gets to see push-up exemplars from different viewpoint and it becomes robust to those viewpoints. Additionally, we use a zero shot latent. So in case like, of course, like during inference, we can never hope to get exemplars. Like if we get exemplars, we are lucky, but we cannot hope for that. So for that, we are using a zero shot latent as well, which is being learned during training. So the zero shot latent acts as a proxy exemplar. So in case you don't have an exemplar, you send a zero shot latent and it will say it will tell the model that you don't have an exemplar, count whatever you find is countable. I will explain everything in details. So these are our contributions. And so this is our architecture. Given a video, what we do is like we have fixed windows and each window has 64 frames. We send it to a pre-trained encoder. We do not train this encoder and we compute the video latents. And after getting the latent for each of these temporal window, we concatenate them in the temporal dimension. So we get an entire video latent in the temporally ordered. We add positional embeddings. As I said, during training, we sample exemplars from the video or from a different video but with the same action. We send the frames to the same encoder. We get the exemplar latents and we do a cross attention between these exemplar latents and the video latents. As I already said, we also use a zero shot latent. So during training, either you can use one exemplar, you can use two exemplars, or you can use no exemplars at all. And in case you are using no exemplars, then you use this zero shot latent and the error will be backpropagated through the model as well as to the zero shot latent as well. And this is how we learn the zero shot latent. So after the cross attention is done, we send the output of the cross attention block to another decoder, which is also transformer based, and finally we get a density map. So how we create this density map? The density map needs to show where the repetitions are occurring. So in the training data, we already know where our repetitions are going on. Like that, we know the start and end of each repetition in a video. We can create this density map like such that the density map is high when a repetition is going on, and otherwise it will be 0. And we also design the density map such that the sum over the density map will give us the count of the repetition. Now, how do we, as I said, like we do an exemplar attention in our model. So our model uses cross attention between the exemplar latents and the video latents. And these exemplars can be from the same video or from a different video. So the exemplars vary in viewing angles or speed or whatever. And this is how our model becomes robust to looking at like different repetitions. So what we do is, let's say we have 2 exemplars, we compute the exemplar latents, we do a cross attention between each of these exemplar latent and the video latent, and then we average over the output and we send it to the next block. So this is like the parallel CS output is an average output of each of these cross attention of the exemplar. Sorry. Slow. So for the decoder blocks, we use windowed self-attention. So we found that normal self-attention does not work well. It generally gives a very uniform density map. So to get a very good density map, we needed windowed self-attention. And for this, we use L-attention blocks, which is equal to 2, as you can read in the paper. And each block is, as I said, each block is made up of window self-attention, along with shifted windows. And we also add an MLP over the self-attention. So this is a standard design of the block. So okay. So as I said, our model outputs a density map. So now we have the ground truth density map, which was created using the ground truth annotations. Like we know the start and end of each repetition in a video, and by that we get this ground truth density map. And we then compute, like for the loss, we compute the MSE between the predicted density map and the ground truth density map. So this also teaches our model to temporarily localize the repetitions in a video. Additionally, we use another loss, like just by temporal localization, we won't be like the model won't be optimized for count, like giving correct counts. So we add an additional loss, which is the absolute error between the predicted count and the actual count of the repetitions. So what happens, another thing that happens is like, because we are creating the video latent by using temporal windows. So let's say one repetition happens in 2 consecutive windows, like part of a repetition happens in the first window and another part happens in the second window. So sometimes the model tends to count this thing as 2 repetitions instead of 1. So this is problematic for us, and for that we came up with a new augmentation called time shift augmentation, which kind of uses overlapping temporal windows, but then ensembles over the output. And by this, the effect of one repetition of like being in 2 different windows is nullified. But so this was all our architecture. Let's look at some results. So previously in video repetition, people have used these metrics, which was MAE and OBO. So the mean absolute error basically says how close is your predicted count to the correct count. And the off by 1 is if your predicted count is different from the actual count by less than 1, then it's considered a hit. Otherwise, it's a miss. But given like the progress of video repetition counting, we think these metrics are very relaxed, because MAE, as you see, like the MAE is division over the actual count, which makes it biased towards the smaller counts. And OBO does not say your model is actually giving a correct count. It says like your count is like the predicted count is off by the actual count by less than equal to 1. So we want our model to give exactly the correct count, not just by one, like a different by 1 or something. And RMAC, and we also propose the use of RMAC. So this is inspired from image counting. And because RMAC is not biased by small or large counts, it treats all the counts equally. Like it doesn't matter how big is your actual ground truth count. So we did comparison with previous baselines on 3 different benchmarks. Like the first one is rep count, which is a very recent benchmark created for repetition counting. This is primarily composed of gym activities such as push-up, pull-up, squats. Countix is a subset of kinetics, which is the biggest repetition counting data set. And finally, we have UCF rep, which is the oldest one, which is a subset of UCF 101. On all these 3 data sets, even if we use the same pre-trained encoder as previous baselines, we outperform them significantly. But what we found is like video MA backbone is the best that works in our architecture. So we propose our architecture with the video MA pre-trained encoder. And one more thing is like in Countix, what happens is like the Countix does not come with ground truth annotations of start and end. They just say in this video you have 3 counts. In this video you have 4 counts, but we do not know the start and end of repetitions even in the training data. So what we do is instead, since we do not have the actual start and end, we create pseudo levels. We consider that the video is exactly periodic, and we divide each the video into equal length repetitions. So if it says like there are 3 repetitions in this video, we divide the entire temporal extent into 3 equal segments and say each segment is a repetition. And this is how we train the model. So even if we train the model using these pseudo levels, ESCounts performs much better than previous baselines. Let's look at some qualitative results. So what we did here is like we plotted the scatter plot for the predicted counts versus the actual count. So the diagonal says like your count, the prediction is exactly equal to the ground truth. So if you see like the trans RSC is one of the recent baselines, and trans RSC does really well for small counts, but as you go for higher counts, it fails. But our model does well for over a diverse range of counts. And these are some visual examples. Like we are also getting good density maps, which means like our model learns to temporarily localize the repetitions as well. So yeah, on the right hand side, I am showing examples for high counts, which is like 52, 58, which are significantly high. And still ESCounts is performing really well. Even though ESCounts fails in some cases, its prediction is really close to the actual count compared to trans RSC. These are some qualitative examples, which are always more interesting than numbers. So if you see this video, the person is doing push-ups and our model is learning to temporarily localize these repetitions correctly. Another video from Countix. As I said, Countix does not have actual start and end annotations. We created pseudo labels for that. So because our model was trained on pseudo labels, it does not temporarily localize the repetitions that well, but still it gives the count really well. Another video from rep count, which is for high counts, and yeah, it localizes even dense repetitions. So another good thing about our model is it is very generic, and even though it was trained for these gym data sets, which are very limited in application, we applied our model on egocentric video, which is first person videos. And even there, so the problems with previous approaches is like they count head motion as repetition as well, but our model learns to ignore this head motion and actually counts the correct repetitions as repeating signals. So this model was trained on dep count, but never saw egocentric data during training. And then we applied the same pre-trained model on egocentric, and still it performs really well. Of course, if you fine tune it, it will perform much better. We following previous works, we tested for generalizability. So one thing about repetition counting is if your model is trained for a particular number of classes, it does not mean that your model has to do only well on those classes. It has to be generalizable. So if your model is trained on push-ups, it should be counting pull-ups or squats or any other activity, for instance. So what we did is we divided the entire rep count dataset into entire rep count dataset based on the classes. So if you have 10 classes, we divided 8 classes for training and the rest of the 2 classes we kept for testing. And we call that set as open set. And in open set as well, the ESCounts is performing much better than baseline. Another generalizability test that we did is like we trained our model on one data set but tested on completely another data set. We already saw these results qualitatively on egocentric data sets, but these if you look at the numbers, it also says like our model is doing much better compared to baselines. And another good thing about our model is like even because it was trained to see exemplars, it can accept exemplars during inference as well. So currently, whatever results I have shown, it is using the zero-shot latent. Because the previous baselines had no concept of exemplars, we felt it was unfair to do a comparison where our model sees an exemplar and counts it. So we only use the zero-shot latent for those comparisons. But if you provide our model with exemplars during inference, it will give you much better performance, and which is evident from the numbers. So we did more ablations. So for example, like are exemplars really helpful? So we removed the cross attention block and replaced it with self attention only. So if you remove the cross attention block, our model won't do any cross attention between exemplars and video latent. So the effect of exemplars is gone. So as you can see, if you do self attention only, it does not do that well, but exemplars help. Another question is how many exemplars should you use during training? So we sample like 0 to 2 exemplars during training. So because of our limitations in GPU memory or whatever, so we could only do this. But yeah, it like having exemplars help. Also, as I said, you can sample exemplars from the same query video or a different video having the same action as there. So we found like if you sample exemplars, let's say if you have a query video where the person is doing push-ups, and if you sample exemplars from another video with push-up where a person is doing push-up in a completely different environment, it helps. It helps our model a lot. And this sampling probability says by how much probability you choose an exemplar from a different video compared to another, like the same video. Density peak. So during creation of the density map, this density peak says how so this controls the sharpness of your density map. And we found like sigma is equal to 0.5 does well. And this is the time shift augmentation, as we say. So we use 4 overlapping temporal windows and ensemble their output. This gives us the best results. And this is just the loss function. As I said, we use 2 components in the loss function, where one is the MSE loss and one is the MAE loss. And we found using both of them helps. So that's all from me. And these are some of the links. Like we already have our paper on archive. This is the archive link, and our code is publicly available on GitHub. You are free to use it. And this is our web page. And these are some qualitative examples. So
Awesome.
if you have some questions, let me know.
Yeah, thanks a lot, Saptarshi. I also put the link to the webpage on the Zoom chat as well. But if you can also put the archive link in the GitHub in the Zoom chat, I think that'd be great.
Okay.
Since we're like running a bit low on time, I think we can move on to the final speaker. But if you have any question, yeah, just put on the Zoom chat, and then I think Saptarshi can answer them asynchronously.
Thank you.
Do you mind stop sharing the screen? Yeah. Perfect. Go ahead, Junho. Awesome.
Okay, thank you for the invitation. And I'm going to introduce our CVPR work on low resource Bayesian challenges for foundation models. Low resource natural language processing actually has been well studied, where many languages lack sufficient data for deep learning at scale. However, there were no previous works in low resource Bayesian tasks. Actually, there were many works that study how to utilize limited label data in computer vision, like meta-learning, few-shot learning, and generative modeling. However, they mainly focus on high-resource image domains, where thousands of images from the same domain are available, even though each class may only have a few samples for model learning. We instead focus on the low-resource vision tasks, where data is scarce, has fine-grained differences, and comes from highly specialized domains. To study this problem, we collect a benchmark for low-resource image transfer evaluation, consisting of circuit diagram classification, historic map retrieval, and mechanical join retrieval. For the circuit diagram classification, given a circuit diagram picture, we want to classify it into its corresponding function, like audio amplifier, audio mixer, and power supply. Here we show some classes with the most samples, like the LED circuit, the transmitter, wave generator, tone generator, and receiver. For the historic map retrieval, given a historic map, we want to find the corresponding satellite map. And we collect the historic maps and satellite maps from different countries, like United States, United Kingdom, European countries, and China. For the mechanical join retrieval, given a 3D render image, we want to retrieve the corresponding 3D drawing and vice versa. We actually have tried our best to collect as much data as we could find freely available online for each task, but the amount of data is still very small, showing how low resource these tasks are. We identify 3 challenges in the low resource region. The first challenge is the data scarcity, and we propose one baseline to generate data by generative models to reduce the data scarcity problem. And the second challenge is the fine-grained differences among images. And correspondingly, we propose one tokenization baseline for fine-grained details. The third challenge is that the low resource image usually come from specialized domains. And we also propose a special attention mechanism for the domain shift. Actually, each of these challenges has been studied in isolation in vision. However, their combination is unique to low resource vision tasks. And our goal is to adapt foundation models pre-trained on large-scale datasets to low resource tasks. For the first challenge of data scarcity, we propose to use generative models to enlarge the data space. Intuitively, given a low resource image, we can send it into a generative model like the diffusion models and get a generated image that is very similar to the input image. We call such images label presuming augmentation. And we can also get some generated images that are very different from the original input image. And we call such images label breaking augmentations. For the label presumed augmentation, we use them in the same laws as the original input images. And for the label breaking augmentations, because we don't have the labels of them anymore, so we use them in the contrastive self-supervised learning laws. And here we show some examples of our generated data. Here we can show the original image and the label preserving image that is very similar to the input. And we also have the label breaking images, although they are very different from the original input images, but they still come from a similar domain compared to the input. So they actually enlarge the data space by using them in a constructive learning loss. And here are some examples for the old maps. And mechanical drawings. For the second challenge is the fine-grained differences among images. And we also observe that for foundation models, they usually have a large convolutional kernel to embed the input image patches. So, and we find that such large kernel actually can ignore some fine-grained details. So we propose a new tokenization strategy. We first divide the original tokenization kernel into subkernels so that these subkernels can be applied onto smaller image patches for tokenization. And we learn a weighting for the subkernels to combine the output to get the final feature tokens, which are sent into the transformer layers. However, there are still remaining challenges. Our methods may focus on prominent regions only, but ignoring other important areas. And our method also struggles on rare patterns. The third challenge is that the low resource images usually come from specialized domains. So they are actually a large domain shift from the natural images. And when we visualize the attention maps inside the foundation models, we find the activations are actually very low. And the transformer attention actually struggles to distinguish the important regions in our low resource data. So we propose to learn a set of global attention maps with common attention patterns, particular to the specialized domain, such as the vertical and horizontal directions for circuit diagrams. Here we show one example of the learned global attention map. For example, for this token in the image, we crop the corresponding map in the global attention map so that this token can focus on its vertical and horizontal regions. And for this token, we also crop the corresponding map so that it can focus on the vertical and horizontal regions. We first test foundation models on our benchmark, and we find that even though ImageBand has generally better zero-shot performance, but the tasks are still far from solved. And we also compare our baselines with previous works. For the baseline for the data scarcity challenge, we compare with previous data augmentation methods, and we show better performance because of the use of label breaking augmentations. We also compare our baselines with previous fine-grained methods, and previous fine-grained methods usually need at least thousands of images for model learning. So we have a better performance by only using around 100 examples. And we also compare with previous transfer learning methods. Previous transfer learning methods also usually use thousands of images for fine-tuning, but we outperform them by using only using 100 training images. And we also combine our baselines with different foundation models, and we show that our method can be easily plugged into different models. Actually, our baselines can recognize prominent patterns in low resource data, such as the coastline in the map of Sydney. However, our predictions can be overconfident, often biasing predictions on one key region, such as the presence of the pedigree in the LED circuit. And we also cannot generalize to rare image patterns, such as the Innsbruck map. Here are our conclusions. We find that low resource vision tasks share 3 common challenges. They are extremely limited data, fine-grained differences between images, and they come from highly specialized domains. We collect a benchmark of low-resource image data and find that foundation models struggle on low-resource vision tasks. We propose one baseline per challenge to make a step towards solving low-resource vision, but the task is still underexplored, with many opportunities for future work. Thank you.
Awesome. Yeah, thanks a lot for quickly going over the presentation. Do you want to put any resources on the chat so folks can take a look? I think I put on the project page, but I think you have to keep up as well. Yeah, any question in Rotown for Yunhua at this point? Maybe like
Here.
Great. I saw some clapping, which I think means you did a good job.
Thank you.
Maybe one question from my end is a lot of the tasks that you help solve, I think you mentioned circuit diagram classification, historic map, retrieval, mechanic drawing, retrieval, right? These are all image based
Yes, image
tasks. Do you think this approach can generalize to like video based tasks?
Yes, I think there are many low resource video data, like like some videos that's teaching math. Such videos, I think, are rarely used in training video foundation models, and also other videos like introducing some chemistry concepts. Yeah, I think there are many low resource video data.
Got it. Yeah, I think that'd be like very useful for us as well. To basically like collecting better data, better low resource video data, so that we can train our video foundation models better. I think that is very applicable. Great. Well, I think if there's no other question for Yunhua, I think we can close up the webinar. Thanks everyone for attending. Thanks to speakers for spending your time going over the talk today. I know for both of you, actually, you call from Europe, right? So it's pretty late in Friday evening. So thanks a lot for staying up late and presenting to our audience. The recording of the webinar will be available probably within 2 weeks or so, and I be sure to share the YouTube link to the speakers so that they can promote it on their social media, different channels, etc. Once again, we run this webinar on a weekly basis, so if you find this useful, informative, would love to have you join next Friday for a few other speakers. Yep. Thanks everyone. I stop the recording now and hope you all have a good rest of your weekend. Bye-bye.
Thank you.